Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing, and this is lecture number 18 where we continue where we left in the previous lecture. In the previous lecture we left with the fact that there will be a change in the intrinsic carrier concentration and the free charge carriers as you go from high temperature to a lower temperature. Now let's look at the left hand side graph here, which plots the number of free charge carriers available with respect to temperature, right, ranging from 700 Kelvin down to approximately few decades of Kelvin, right, around 10 Kelvin to 20 Kelvin. Now if you look very carefully at relatively high temperature, when you do have intrinsic semiconductor available with you, there is no doping possibly at this particular point. Then so there are three regions. One is known as the intrinsic region, right, then we have an extrinsic region, and then we have a partial ionization region. Now in the intrinsic region, which is at high temperature, so there are two regions of intrinsic. One is this one, which is high temperature. As the temperature goes on increasing, right, there is almost an exponential growth in the number of charge carriers, and this is primarily because of the thermal generation or electron hole pair generation. Why? Because now you see you have this conduction band and valence band, right. You just go on increasing the temperature, you will have more and more charge carriers being pushed from valence band to conduction band, and therefore the charge carriers will go on increasing drastically, and that's the reason you see this blue curve going very high. We will discuss about the black curve later on, but the blue curve is going high. As you now go towards a lower temperature, a time comes when typically around 100 to around 500 Kelvin, where the number of charge carriers are fixed because all the dopant species has fully given its charge. So let us suppose you are not doped with 100 atoms of electrons of say group 5 element, which is phosphorus. So what will happen at even 300 to 500 Kelvin, all the dopant species will be giving you all the electrons, and therefore it always remains constant, right, because you are not adding anything extra rather than those 100 dopant species. So with respect to temperature, it almost remains constant for long duration of temperature range. Then as you lower the temperature below 100 Kelvin, now you have incomplete ionization of the dopant species. The last problem in my previous lecture will make you understand this point, that as my temperature was 200 Kelvin there, I went up to 90% of ionization, right, and therefore as I reduce my temperature, the ionization reduces and the number of carrier reduces, and therefore there is almost an exponential drop here with respect to temperature. So we have three regions: partial ionization, extrinsic and intrinsic, and at each places they have this. Now let's look at the black curve. Black curve is basically the Ni curve. Ni curve is the intrinsic carrier concentration. This is not with the dopant species. This is intrinsic carrier concentration. They follow exactly the same trend as the intrinsic region, high temperature region, but as you lower down, the intrinsic carrier concentration starts to drop down, right. And the reason is very simple, because you don't have enough species or enough temperature to actually generate that many number of intrinsic carrier concentration. So the intrinsic carrier concentration goes down, and what we are doing here is we have doped the silicon with 5 into 10 to the power 14 donor atoms per centimeter cube. That's the extrinsic part, which is this one, and this is without the dopant species. So this is with the intrinsic one, and it goes on falling as you reduce the temperature. So two curves we have seen here. This blue curve is basically the one which is having a dopant species. The black curve is the one, dotted curve is the one which is the intrinsic carrier concentration behavior without the dopant species. So without the dopant species, the fall is at much earlier temperature, whereas with dopant species the fall is at much lower temperature. So an n-type or a p-type semiconductor, you will see such a degradation in the number of charge carriers. Now let's look at basic concept here, that if I change therefore the doping concentration, right, or temperature, then how does my Fermi level position changes with respect to the conduction band and the valence band edge, right. Now very simple, because if you remember, from where did I obtain the Fermi level concept? I obtained it from basically the electron and hole concentration at thermal equilibrium. Let us suppose T equals to 300 Kelvin. That's what is written in the first bullet head, that the position of the Fermi level within the band gap can be determined using what? Using thermal equilibrium, electron and hole concentration. So thermal equilibrium primarily means that you are giving, let us suppose 300 Kelvin, the room temperature is 300 Kelvin, and you are giving 300, but the species where you are trying to find out the Fermi level position is also maintaining the 300 Kelvin. It is not rising, right? So temperature is not rising. The thermal equilibrium, dynamic equilibrium is being set up. Now, if you do some manipulation and approximation, then we get that N naught equals to Nc. Nc is the conduction band density of states, exponential kT minus Ec minus Ef, which you get, right? Ec minus Ef. Ec minus Ef is basically the difference between the conduction band edge and the Fermi level. So, if let me give an example. Therefore, if my Ec is very close to the Fermi level, then Ec minus Ef, right? Ef will be a very small quantity. Therefore, the subtraction of these two will be a large quantity, and therefore N naught will be larger. Closer to the conduction band edge, higher will be the number of charge carriers involved in this case. Now, if you solve for Ec minus Ef, I get Ec minus Ef equals to kT ln of Nc by N naught. N naught is the number of charge carriers per unit volume because of the doping concentration, and that gives you a brief, very good idea. Let us say you go on increasing the value of N naught by increasing more and more dopant species. This quantity will go down, right? And therefore, the difference between these two will go down, and Ef will be moving closer and closer to the conduction band. So, just by looking at the position of the Fermi level, I will be able to find out these variations. Now, let us assume that I have put in a dopant atoms whose value is much larger than the intrinsic carrier concentration. So, Nd is much larger than Ni, right? Nd is much larger than Ni. Then of course, what will happen? N naught, which is the number of charge carried with dopant species, will be approximately equals to Nd. I hope you agree with this point. So, let us suppose there were 10 intrinsic carrier concentrations, and I doped with 20 donor species, then the total number of electrons available will be 20. So, that is the reason I have written N naught to be approximately equals to Nd. And therefore, what you write down, you replace N naught by Nd, so you get Nc by Nd. So, Ec minus Ef equals to kT ln of Nc by Nd, right? Nc by Nd is the number of donor species which you get, and Nc is the concentration, sort of the density of state concentration in the conduction band. And there, as simple as that, Nd again, if it increases, this quantity goes down, and therefore Ec minus Ef goes down, primarily meaning Ef is becoming closer to Ec. And that is what you see, that the distance between the conduction band edge and the Fermi level generally follow a logarithmic function of the donor concentration. So, it is not a linear one, please understand, it is a logarithmic one, which means that more species, if you go on adding, the distance goes on reducing. So, more and more it goes closer to the conduction band, more and more it goes. Now, I leave as an example or a question to you is, what will happen if the Fermi level crosses the conduction band and goes into it crosses the conduction band edge and goes into the conduction band? How will the device behave, or how will the semiconductor behave in that case, right? You should be aware of that particular thing as well. Now, as I discussed with you, therefore, second point, as the donor concentration increases, the Fermi level becomes closer and closer to the conduction band. So, takeaway from all this discussion till now is, at lower temperature, I would actually see there will be less number of carriers, less number of free charge carriers, and at lower temperature there will be another problem that you will have. Therefore, this is known as freeze out, and therefore, and also we learned that Fermi level is a function of the difference between the conduction band and Fermi level is there, right? Now, let us look at the same expression here. Fix the value of Nd. Let us look at this expression here. Fix the value of Nd and Nc. Nc is always fixed, Nd is also fixed, and I have therefore Ec minus Ef equals to kT ln of Nc by Nd. Now, so you see, Ec minus Ef has a linear dependency on temperature, is directly proportional to temperature. So, as the temperature goes on reducing, the distance between Ec and Ef goes on reducing, which means that I will have a higher probability of finding electron in the conduction band, because the distance between the Ec and Ef is increasing. But please keep in mind that your N naught is also reducing because of the reduction in the number of donor species participating in the free charge carrier movement. So this is sort of a optimization problem where I cannot just say that by reducing the temperature I will be able to achieve a larger number of carriers. No. Yes, if Ef will go closer to Ec, that is agreed, but then your Nd will be falling down to a very larger extent. The donor species will fall down to a larger extent, and as a result Ec minus Ef will go on increasing in that case. So you need to take care of all these aspects as far as understanding or evaluating the number of free charge carriers in the species are concerned, right? Now, I have already told you, and this is the same one which we are doing. So, if the Fermi level is closer to the conduction band edge, concentration in the conduction band increases. I have just not discussed all those points to a detailed one. Now, let us look at what is known as a compensated semiconductor. Now, I will tell you what is a compensated semiconductor. I will give you an example. Let us suppose I first push in 100 number of donor species into the semiconductor. So, there are 100 atoms of phosphorus group 5 element inserted into semiconductor, right? So, and I am assuming 100% ionization. So, all those 100 number of donor species have donated 100 electrons to the conduction band, and therefore, the number of free charge carriers, especially electron in n-type semiconductor, has become 100 now. But what I did also was, I also inserted 50 amount of acceptor ion concentration, let us say a boron. Once I do that, the effective number of electrons available to me will not be now 100, but it will be 100 minus 50, and therefore 50 will be the number of electron. And that is the reason you see that Nd has to be replaced by Nd minus Na in the compensated semiconductor. So, compensated semiconductors are defined as those semiconductors where you do, first of all, you do a group 5 and then you do a group 3, right? Or otherwise you do group 3 first and then you do a group 5. Either of the two cases you do. So, what will happen? We can very well understand, if Nd becomes equals to Na, right, then Nd minus Na will be equals to 0. Nd minus Na will be equals to 0. And what will happen? The Fermi level will actually shift to the intrinsic Fermi level, because you are achieving the old sort of mechanism here. That is what the whole idea here is being shown here. So, what I am showing here is the difference between the Fermi level and the intrinsic Fermi level on the y axis, and the temperature on the x axis, right? And let's because 300 Kelvin is which we are most familiar with, and this is my conduction band edge and this is my valence band edge. My conduction band edge is at 0.6 EF minus EF. So, this is my conduction band edge here, and this is my valence band edge here, right? Now, we have told you EC minus EF will be KT by Q ln of NC by N naught, right? For an n-type semiconductor, I can replace N naught by Nd. So, I get EC minus EF equals to KT ln NC by Nd. Now, you see, if you at 300 Kelvin, right, let us suppose your intrinsic carrier concentration was, let us suppose 10 to the power 18, right? You lower the temperature. As you lower the temperature, the intrinsic carrier concentration reduces and EF minus EI reduces, which means that EF is coming closer to EI, right? EFI. EFI is the intrinsic Fermi concentration. So, let us suppose you are trying to find out EF minus EFI, then what we see is as let us suppose at 300 Kelvin for intrinsic carrier concentration of 10 to the power 18 with us. As you lower the temperature, this goes to the left, and as you can see, it is going down and down and down. More easy will be for n-type to understand. Let us take up any one of them. Let us take this one, let us suppose, right? This is 10 to the power 16. At 300 Kelvin, you have concentration for 10 to the power 16, and EF minus EI is somewhere around 0.2, 0.3. Let us say EF minus EFI is equals to 0.35 electron volt. Now, what has happened? You reduce the temperature to 100 Kelvin. 100 Kelvin, it is somewhere here at the top, which means that EF minus EFI has actually increased, which means that EF has actually gone away from EFI. EFI is a fixed value, no, 1 by 2. But what has happened is, for a fixed value of 10 to the power 16, at reduced temperature, this has gone high. Gone high effectively means that my Fermi level has moved away from the intrinsic carrier design. That is what we have seen also in the previous slide also, that it will be closer to the conduction band edge which we see. And this is for silicon, for both conduction band as well as for the valence band we have shown, and that is what is known as conductivity, right? Now, let us take up electron concentration on the y axis and 1000 by T per Kelvin as on the x axis. So, as you move from right to the left, you are lowering the temperature. Now, the conductivity is defined as E mu P into P for a p-type semiconductor. E into mu P into P, sigma, which means that the conductivity depends on the electron concentration, it depends upon the mobility of the charge carriers, and it also depends upon the intrinsic value of electrons. So, it is basically Q into mu P. If you would have taken an electron, then this mu n would be equals to Q times mu n times n, right? That we would have told. Now we already know from my previous discussion this as the graphical functionality of electron concentration with respect to temperature. We have already seen that in our previous discussion, or even the first page of our the first, yes, this one. If you look, the same thing is replicated almost in the same manner in this one, in this graph, right? So what is happening as you make the temperature go lower and lower, the electron concentration is lower. We have seen that, no worries on that. What happens is, therefore, the sigma value, which is the conductivity value, actually shows. So let's not go for higher temperature to make the conversation restricted to 300 Kelvin and below. So let's take up a 300 Kelvin design here. So at 300 Kelvin, this is your sigma value, or the conductivity, right? Conductivity is how much? Approximately equals to 0. This is a log scale, so it's 0.01, let us assume. Now as you go on reducing the temperature, the conductivity starts to increase. Why it increases? Because your mobility starts to become larger and larger. As you lower the temperature, there are less amount of collisions, there are less amount of scattering, mobility tends to increase, and that's the reason you see almost an exponential increase in the value of conductivity. Till 200 to 250 Kelvin, you will see such a change. Beyond that, as you further lower it, the intrinsic carrier concentration reduction, which is the blue line, dark blue line, that takes over. So this quantity then drops down. So though this quantity is slightly increasing, this drops down drastically, and that's the reason your sigma starts to drop down. You got the point? The overall understanding, I hope it is clear to you, that what two things, we'll go below 300 later on, but let's concentrate on 300 Kelvin and below. So at 300 Kelvin, let us assume that my sigma is 0.01. As I lower the temperature, right, my conductivity starts to increase or improve. The reason being that nothing is changing too drastically, but what is happening is I have an increased value of mobility. Why? Because the number of charge carriers available is not changing drastically. You see, the number of charge carriers in this region is almost constant. This is almost constant, you see. So that is not changing. So this quantity is not changing. What is changing is that mu p is, or mu n is increasing. As it increases, the conductivity increases, and that's the reason you see the conductivity increasing here drastically. It crossovers, and then somewhere around 150 to about 120 Kelvin, the carrier concentration itself shows a dip, and therefore this quantity shows a dip, and that's the reason your sigma shows a dip. So this is the overall trend of a conductivity versus temperature. So you are asking me why this is being taught to us. The reason being, you need to know how the carriers flow at various low temperature, and that's the reason this is discussed with you in this case. Let's take up a numerical example here, a numerical approach here, right? And let's take up how we can manage the numerical part of it properly. So the question is that you need to determine, you are told to determine the doping concentration and the majority carrier mobility for a compensated semiconductor, right? Compensated. So it's basically compensated n-type semiconductor, which means that I had initially some dopant species, I had added acceptor ion concentration, but still remaining n-type silicon at 300 Kelvin. Conductivity is given as 10 to the power 16 ohm centimeter per, and accepted doping concentration of 10 to the power 17 centimeter. So what they are saying is find the donor concentration and the electron mobility. We already know that we are trying to calculate all these discussion at T equals to 300 Kelvin. We now assume at 300 Kelvin, it is safe to assume that you have complete ionization. So this is primarily 100% ionization which is happening, right? You have 100% ionization, and therefore Nd minus Na will be much larger as compared to Ni. Why? Because since it is a compensated semiconductor, Nd minus, you will not have Nd now, you will have Nd minus Na. Why? Because you did initially say 100 amount of dopant species, then you put 50 amount of acceptor species. So the effective value of number of electrons will be 100 minus 50, which is 50. Assuming 100% ionization, I would still say that this is much larger as compared to Ni, and we are assuming it to be a fully ionized, which we get, and therefore we put back into the same equation which we learned just now. At 10 to the power 16 it will be there, and this is Q value mu n into Nd minus 10 to the power 17. If we choose Nd equals to 2 into 10 to the power 17, then we get Ni to be equals to Nd plus Na. What is Nd plus? Nd plus is the number of dopant species which have actually donated electron to the system and itself become positive charge. So, this is in Nd plus, and accepted ion concentration is those which have actually accepted electrons and itself become a negatively charged. And we find that this 3 to the power 17, if you place that value inside the previous equation, I have a mobility of 510 centimeter square plus volt second. This is for Nd equals to 2 into 10 to the power 17 per centimeter cube. Now, if you choose Nd equals to 5 into 10 to the power 17, then what we get is we get mu n is equals to 325 millivolts centimeter square plus volt second, and therefore that gives me a sigma value of 20.8 centimeter per 1, which means that therefore if I assume that the doping is bound between 2 into 10 to the power 17 and 5 into 10 to the power 17, then we can find out that the mobility happens to be approximately equals to average of 510 and 325, approximately equals to 400 centimeter square plus volt second. And if you take this quantity and this quantity, I will get a fresh value of sigma as 16, which you get. So, we started with our initial value of 16 and we ended up with initial value of 16, assuming that 100% ionization has taken place and the doping concentrations are exactly the same in both the cases, right. So, with this let me recapitulate what we did in this expression, or in this one. We looked into how my Ni varies with the function of absolute temperature T in Kelvin, and I saw there were 3 regions, 1, 2 and 3. The first region is intrinsic, right, the second region is extrinsic, and the third region is also referred to as incomplete ionization region. Intrinsic, extrinsic and incomplete ionization. Then we came to the fact of conductivity and how conductivity is related to the doping concentration and temperature. We also looked into the fact that if you are plotting conductivity with respect to temperature, why and how is it changing with various values of temperature beyond 300 Kelvin. Please try to do it below 300 Kelvin. What is the function? Above 300 Kelvin, what is the functionality? And there you will see the conductivity. If you look carefully in the previous slide here, I didn't discuss that, but if you look here, conductivity again shoots up, right? And this is primarily because large generation of electron hole pair takes place. You see this suddenly rising up. This sudden rising up comes with the sudden rising up here, right? So, that gives you an idea about the intrinsic carrier concentration here. And then finally, we ended up with a numerical problem to showcase how does the mobility and the number of charge carriers affect the total concentration and the conductivity. So, I hope you enjoyed this lecture. We will meet next time in the same platform. Thank you very much.